Hi everybody, I am Gabriele Gaiti and I am a PhD at the Vancraft Laboratory at NTNU. And in this presentation, I'm going to briefly explain the topic of my PhD. So in the last century, we have assisted to an almost exponential increase of the energy consumption. And in the recent years, to follow the increased energy demands, incentives have been introduced in a form of a more favorable price scheme. This more favorable price scheme has led to an increase in the profitability of running hydropower plants while following the price fluctuations. While the price demands fluctuating, the production of hydropower plants can fluctuate too. As we can see in the picture in the top left corner, the energy consumption has exponentially increased through 1960s. While in the main picture in below, we have seen the variation and the fluctuation of the price of energy, especially during the energy crisis of the last year. This has resulted in an increase of the operation in the time so-called off-design conditions, meaning condition in which the flow regime is not optimal for the design characteristic of the hydropower runner. So in a reaction turbine as a Francis, this, together with the further development of runner design, which has led to a more efficient, cheaper and thinner runner blades, has resulted in an increase of the vulnerability on phenomena happening on off-design conditions, resulting in an increase of runner cracks or failures due to mutual interaction between fluids and the structures. As we can see in the pictures, from the left we have three types of failures. We have a small failure, just the runner cracks in the utmost left. We have a big piece of turbine that has been missing in the middle one, while we have a catastrophic failure of the entire runner in the utmost right. But one of the main phenomena causing runner failure is resonance, which destructive power is already well known in civil engineering, and a famous example is the Tacoma Bridge. So in a coupled system composed by a fluid and a structure, the movement of one of the two would be dampened by the other. But when the interaction of the two results in an oscillating force, if the frequency of the oscillations coincides with the resonance frequency of the structure, we will assist in an uncontrolled amplification of the fluctuation, generally resulting in structural failure. This concept applies to hydropower runners too. So runner designers always perform a resonance analysis in order to check that the runner they've designed will not experience resonance condition for the flow design which is designed. But when the flow condition changes in a so-called part load regime, maybe due from the reason from before, the runner could suffer resonance regime, resulting in cracks or failures. For part load regime, we mean condition in which the flow is lower than the one the turbine has been designed for. So to determine if a runner will fall in resonance regime for a specific flow is not trivial. The damping given by the water is dependent on its velocity, therefore flow dependent, and on the specific configuration of the runner system itself. So higher velocity generally gives higher damping. Therefore, especially when going from full load to part load, runner can experience higher vibration than expected. This is due to the decrease of the flow and the related decrease of the hydrodynamic damping on the runner oscillation. But to make a proper analysis on the real Francis runner is very complicated, as multiple phenomena happens at the same times, and is not trivial to decouple the participation of the single phenomena. Moreover, damping is dependent not only on the velocity, but also on the shape of the runner, and also of the shape of the fluctuation itself, also called modes, as you can see, for example, in the top right picture. So a simplification of the system was necessary, and studies on hydrodynamic damping were made on single linear hydrofoils and linear cascade. These studies have shown the same trend for both the configurations, on which specifically before the lock-in region, which is defined as the region where the vortex shedding coincides as the natural frequency of the structure, the hydrodynamic damping is almost constant, while after the region of lock-in, the hydrodynamic damping is almost linearly increasing, meaning that the hydrodynamic damping is increasing with the flow velocities. So the question that followed was, what is the effect of neighboring structures on the damping? So the goal of my PhD is to understand the damping behavior in a non-rotating radial configuration of pinnal hydrofoils as a further step in order to understand the damping behavior in a complex system as a Francis turbine. So in order to achieve the goal, we planned a detailed measurement of the prototype damping through different flow velocities to the main modes of vibrations. The prototype had been equipped with strain gauges, pressure sensor and piezoelectric patches in order to control the excitation of the blades. Moreover, the prototype has been designed to have optical access in order to allow flow measurements as PAV and LGVs. And a second campaign of measurements will be done, including PAV analysis of the flow downstream the cascade, and it will be used to validate the numerical simulation of the coupled system. So on the right, you can see the prototype model from both CAD and the one actually in the hydropower lab, while in the left you can see how is the sensoring made on the blade itself. So the results obtained so far includes a PAV flow measurements of the wake flow downstream a single hydrofoil from which the damping results were already extracted in previous works, a model analysis of the oscillation shapes in both air and water for the prototype I'm going to test for damping, and an instrumentation of the blade cascade that is now getting ready for the actual damping measurements. So, in conclusion, a full understanding of hydrodynamic damping could potentially provide the future runner designers the tools to design blades that are not affected by resonance problems, as the resonant peak could be smothered by the hydrodynamic damping actions, avoid expensive runner repairs and/or replacements. Thanks you for your attention.